Hi, welcome to the second video for week 7. In this video we're going to look at derivatives of exponential and log functions. So these are a couple of rules that you need to know, so you might want to write these in your books. But for the derivative of e to the power of x, remember e is just that number there, 2.718. The derivative of e to the power of x is just e to the power of x. Nice and simple. The derivative of an exponential function, a to the power of x, is given as a to the power of x log a. So just the same as up here. The natural log of e is 1, so we don't need to worry about the log when we're using e. So that's for e to the x, that's the general form. We're going to use those now to solve some derivatives using the product rule, chain rule, quotient rule, just as we have before. So in this the first example, we're going to look at the derivative of x squared times e to the power of x. Now because these two terms are being multiplied, we can use the product rule. So just as we've looked at many times before, when terms are multiplied, we can use the product rule. Let one term equal u. Derivative of u is 2x. Let the second term be v, which is e to the power of x. The derivative of e to the power of x is just e to the power of x. Putting those together using the chain rule, which is what we have written here, gives us x squared times e to the power of x plus e to the power of x times 2x. And because we have common terms here of e to the power of x and x, I've taken those common terms out and factorized it, and we have a final equation of x times e to the power of x, brackets x plus 2. Now hopefully these should be fairly straightforward for you by now. All we've done is introduced a new term with our derivatives. Same procedures still apply. Second example is find the derivative of 5e to the power of 4x. Now we know what the derivative of e to the power of x is. What we don't know is the derivative of e to the power of 4x. So in cases like this, just like when we had with sine and cos, we need to use the chain rule. Now we let u equal that index there. So in this case, we're going to let u equal 4x, and the derivative of u with respect to x is 4. So we can rewrite the equation as y equals 5e to the power of u. Now we know what the derivative of e to the power of u is. It's just going to be e to the power of u. The constant stays the same. It's not affected. The coefficient, not the constant. The coefficient 5 is not affected at all, so the derivative of y with respect to u is just 5e to the power of u. Now with the chain rule, we multiply these two values together to find dy dx. So we multiply those together and we substitute our value for u, we get 20e to the power of 4x. Again, not too dissimilar to what we looked at with sine and cos, just need to use that chain rule if we have an index that is not just x. And the third example we're going to look at for exponential functions is 5 to the power of x times cos x. So again, we're multiplying, so we're going to use the product rule. And we're also going to make use of this derivative property that we looked at at the beginning of the lesson. So the derivative of a to the power of x, so in this case our a is 5, is a to the power of x natural log of a. So we're going to use that, and like I said, we're going to use the product rule. So we'll let u equal 5x. So using this rule over here, the derivative of u is 5x times log 5, and v equals cos x, and the derivative of v is negative sine x. So again, just applying our product rule down here by multiplying u and v and the derivative of u plus u times the derivative of v, we get this line. Again, we've got a common factor, 5 to the power of x, so we can take that out and factorize, and we're left with 5 to the power of x log 5 cos x. Now remember, log 5 is just a number, but it's just a bit neater to write that rather than the decimal, minus sine x. So again, this one here, we've had the product rule plus our definition. In the previous example, we used the chain rule as well. So just using those rules in our derivatives just as we have before. Now moving on to log functions, log to base e, remember that is just the natural log, and the natural log of x is 1 over x. Now the general form is log to base a x equals 1 over x log a. So again, record these in your books, and we're going to use them. You need to be familiar with them, and we're going to use them in a few examples now. So the first one, we've got y equals log to base 4 5x. We're just going to use those properties we just discussed before, or that derivative rule that we just talked about before, in addition to the chain rule. So we have we let u equals 5x, so the derivative of u with respect to x equals 5, and then we also have so we can do our y equation to be log 4 base u, log base 4 u, and the derivative of that using our rule, our log rule up here, is 1 over u to times log 4, natural log 4. I should just go back, and the reason we need to use the chain rule is because of this 5x here. It's not just x. So with our rule, we can only apply it if we just have, we don't have a coefficient there, it's just an x. Here we've got 5x, so we need to use the chain rule to get rid of that 5x and just make it a u with no coefficient out the front, or a variable with no coefficient. So again, we just use the chain rule and that log rule. And so we bring those two together, we multiply those du over dx and dy over du. We get 5 times 1 over u log 4. Remember, u equals 5x. So when we substitute the u back in, or 5x in where u was, the 5's cancel each other out, and we're left with 1 over x log 4. So again, not too dissimilar to what we've seen before. It's just introducing a new property here, a new derivative property or a new derivative rule that we know, which is logs to a base, but we're still using the chain rule and just working our way through that. Now this is the final example we're going to look at. We're going to find the derivative of log x squared. Now there's a couple of methods we can go about finding this. I'm going to run through both of them. The first is probably what we're more familiar with, and that's using the chain rule. So again, we only know the derivative of log x, where there's no additional power. So we're going to need to use the chain rule. So we let u equal x squared, meaning du dx equals 2x. We rewrite our initial equation as y equals log u, and we know the derivative of natural log u is just 1 over u, and so we can use the chain rule, multiply these two values together, and we get 2x times 1 over u. Substituting u equal x squared in, we get 2x over x squared. The top x and the one of the x's on the denominator cancel each other out, and we're left with x over 2. So again, using the chain rule, making use of the log laws, the derivative of natural logs, to find the derivative of that expression. The second rule is actually going to use the fact that natural log of x squared equals 2 times the natural log of x. So this is what we've looked back when we were solving exponential equations and log equations, realizing that that property exists, we can rewrite y equals 2 log x. We know what the derivative of log x is. Derivative of log x is just 1 over x, so our answer becomes 2 times 1 over x, which is 2 divided by x. So, same answer, 2 different methods. Just need to make that realization that log x squared can be written or simplified down to 2 log x. So that's the end of this week's video. Again, you need to take these rules and these properties of logs and exponentials and apply them to find the derivatives of different equations, and that's what we should be working through this week.